Hello and welcome again to my Physics Online video series. Today's video lecture we're going to be talking a bit about semi-constant acceleration. Now this kind of bears a little bit of maybe explanation before we actually get into the lecture proper. What do I mean by semi-constant acceleration? Basically, we have at this point been talking about motion with constant acceleration and the description of kinematics with constant acceleration, but we can actually go a step further and allow the acceleration to change as long as it changes without being continual change. So what I mean by that is that I have an acceleration that is constant for some duration of time, and then at the end of that duration maybe the acceleration changes to a new value and is constant at that new value. Okay, and we can still handle motion with those kinds of changes algebraically. If it's continually changing, then for the most part we can't handle it, and we certainly can't handle it with the equations that we've derived so far, with the concepts we've derived so far. We will in the future actually experience what does it look like if you have continually changing acceleration of one type, which is oscillatory motion. But that's not really for this particular set of lectures. Instead, we're still wanting to consider motion that has more or less constant acceleration. We're just allowing the acceleration to change a few times in that more or less. So we begin, as we so often do, by reviewing a couple concepts from previous videos, previous lectures. And what we specifically want to review here or recall here is motion with constant acceleration. And what we want are to refresh ourselves on what the equations are for displacement or for position and for velocity versus time. So motion with constant acceleration. Our position versus time equation would look like this. Position is given by, and the order of the terms doesn't matter, but I like to keep them in some semblance of order. We'll go from lowest power of t to highest in today's. So initial position plus initial velocity times time plus half of that constant acceleration times time squared. All right, our velocity versus time equation should look like our initial velocity plus our acceleration times time. Our acceleration obviously just is constant, and that's the whole point of having constant acceleration for motion. And we can also do this other scalar equation that lets us figure out how far the object has traveled using the final and initial speeds, which is written sometimes like this and sometimes with the subscript of an f on that first v. Alright, so this all assumes that we have a constant acceleration. Okay, note that the velocity is not constant, the position is not constant, but the acceleration is constant in some way. So the question that we're kind of looking at today is, what if the acceleration can change, but change such that it's still constant over a given interval with changes at certain intervals? And a picture is sort of worth 1,000 words on this one. What would that actually look like? Maybe it's easiest to see in the form of a set of plots. So as I so often do, I show you the kind of code that I've written in order to make these plots. So, you know, if you're watching from home, you're welcome to like screenshot it, copy it, modify it, whatever. This is written up in Octave. It ultimately plots velocity versus time, acceleration versus time, and position versus time, actually in that order. But for the purpose of framing this, let's just look at the acceleration versus time graph. So this is your acceleration versus time graph with semi-constant acceleration. It basically looks kind of like a set of stairs. Although it need not just be a set of stairs. If we come back and change the accelerations a bit, it could be that we let them all be the same value. For example, like here I've got it stepping down from 0.6 to 0 to negative 0.4. I could have it step back up to 0.6, for example. So instead of having something that looks like this, I would now have something that looks like this. Okay, so it doesn't have to literally look like stairs. They also don't have to necessarily have the same time increment for each step, although I just kind of wrote the code in that way this time. You can modify that if you'd like. In any case, I'm going to go back to the original one that I had, which has this as negative 0.4. And what I'm going to do is I'm going to throw the velocity versus time graph for us. So here's the velocity versus time. This is a one-dimensional motion that has the semi-constant acceleration versus time to it. And essentially, one question you may ask is, could you have predicted this from that acceleration versus time, or could you have predicted the acceleration versus time versus from this velocity versus time? And the answer is, for the first question, could I have predicted this exact velocity versus time graph from that previous acceleration versus time? The answer is actually no. I need one more piece of information. And the reason why is because that initial acceleration versus time graph that I showed doesn't actually tell us what the initial velocity is. In other words, where should this thing start on velocity versus time? As it turns out, I have it starting at 2 meters per second rather than 0 meters per second. I could have started at 8 meters per second. It could have started at 1,000 meters per second. It could have been moving in the opposite direction. We have no way of predicting that from just an acceleration versus time graph. We need an initial condition. Now, can we get the acceleration versus time graph out of this velocity versus time graph? Well, the answer is yes. We just need to pick like 2 points that are on this velocity versus time graph, and then get the slope, and then pick 2 more points, and then pick 2 more points. Up here, obviously, the slope is 0. So slope equals 0 here. Slope right here is equal to 5 minus 2, that's in meters per second, divided by 5 minus 0, and that's in seconds. Where am I getting these from? Well, this velocity is 5, the time is 5. This velocity is 2, the time is 0. So 5 minus 2, 5 minus 2, rise, divided by run, 5 minus 0. And that comes out to 3 over 5, which is 0.6 meters per second squared. And I could do likewise over here by picking 2 points on this one to get the slope. So this point right here is 25,6, and that's in seconds and meters per second. And this one is in 30,4 in seconds and meters per second. So the slope for this section would be 4 meters per second minus 6 meters per second divided by 30 seconds minus 25 seconds. And so that slope over here is equal to negative 2 over 5, so that's negative 0.4 meters per second squared. So if I were to put all those things together into a coherent plot, I would in fact get basically the plot that I have right here that I was showing before for acceleration versus time. So let's just kind of copy that over into here. And so this matches, this one matches, this matches the previous graph. And it does so by taking slopes. Now how do we go the other way? What's the other way? The other way is getting from, say, this graph to the previous graph, or getting from the previous graph to position versus time. Well, the answer is that we take area under curve. So over here, slopes give accelerations. Now I would like to discuss what happens if you want to kind of go in the opposite direction. So I've kind of looked at how do you get from this velocity versus time graph to an acceleration versus time graph by taking slopes. Now what we want to know is, can we extract from this position versus time, or at the very least displacement versus time? And the answer is yes, at least yes to the displacement versus time. The position versus time, we would maybe need an initial position. So how to get, let's say, displacement versus time? And the answer is get areas, find areas under the, we could call it lines or curves or whatever. So area or areas bounded by the line or curves, and the axis, of course. So we could say V versus T. So you may be looking at this graph and saying, gosh, this graph doesn't look the same as the graph that you showed earlier, which is this graph. And you are right, I have made a slight change. Namely, I'm just showing more of the plot area. The reason for this is that when we were going from velocity versus time to acceleration versus time, I needed to take slopes. And so it didn't especially matter kind of like where is the time axis located. But for this one, it does matter. We do need to know where the time axis is, because what we're doing is finding areas that are bounded by this set of lines and the time axis. In other words, if I want to know the total displacement from 0 to 30 seconds, I have to find the area that I'm shading in right now. Like this whole shaded area would be the displacement from 0 to 30 seconds. So I will write that area is delta x displacement, and it happens to be 30 seconds because we went from 0 to 30, but in principle we might have shaded only a portion of this. For example, maybe I decided to find from 0 to 25 seconds or something like that. So in that case, the shaded area would be the displacement between 5 and 25 seconds. So we could say from T initial to T final. So here's T final, here's T initial. So let's actually do this, and let's do it for the entire 30-second part of this motion. So how do you find that area? It's actually fairly straightforward. What you do is you basically just break it up into right triangles and rectangles. So there's a right triangle here, there's a rectangle here, there's a right triangle here, there's a rectangle here, and then this whole big thing is also a rectangle, so we could break it up like this, or alternatively we could say there's a little rectangle here, there's a big rectangle here, there's a little rectangle, whoops, or a medium-sized rectangle here, and then there's a triangle here. This is also a right triangle. Either way is fine. You just are wanting to break it up into shapes whose areas you know how to find. So rectangle, you know, the area is just base times height. And for a right triangle, your area ends up being half of base times height. Okay, and so making this shape into rectangles and right triangles allows you to find the area fairly simply. Okay, so for example, this triangle would have a height of 8 minus 2, which is 6 meters per second. It has a base of 0 to 10 of basically 10 seconds. This one has a height of 2 meters per second. This right here has a base of, again, 10 seconds, and it has a height, of 8 meters per second. This one right here has a height of 4 meters per second, and both of these have a base of 10 seconds. This one also has a height of 4 meters per second. Okay, so making use of all those, let's label these. This one right here, this portion has an area of A equals 1/2 times 6 meters per second height times 10 seconds base. So half times 6 is 3 times 10 is 30. So we have an area of 30 meters. This one right here has an area of 2 meters per second times 10 seconds, which is 20 meters. This one right here gives me an area of 8 meters per second times 10 seconds. So 10 seconds, that's 80 meters. This one would have an area of 1/2 times 4 meters per second times 10 seconds, which is 20 meters. This one has 4 meters per second times 10 seconds equals 40 meters. So if I want to find the total displacement for 30 seconds, I just add all these areas up. So delta x would essentially be like the sum of all these areas. So 30 plus 20 is 50, plus 80 is 130, plus 20 is 150, plus 40 is 190. So we expect it to be 190 meters for 30 seconds, or first 30 seconds. Okay? So we can double check that, of course, by plotting it. This is what the plot of displacement versus time would look like. If I wanted position versus time, the only thing that would change is that the whole thing would either shift up or down depending upon initial position. But most importantly, this right here is 30 seconds. This right here looks like it could be about 190 meters. This is 150, this is 200, so 190 is within the margin of error of eyeballing this graph as a nice little double check. There's one other thing, or maybe I should say two other things that could be done with the graphs that I've shown, which would be getting the average value. So like this one, we have velocity versus time. If I want to know what is the average velocity, how would I go about doing that? And if I wanted to know the average acceleration, how would I do that? Well, the average acceleration, I would just simply pick this point here and this point here. So 0, 2 and 30, 4. And I'd find the slope of the line running from one to the other. And that would give me my average acceleration. So A average is 4 meters per second minus 2 meters per second divided by 30 seconds minus 0 seconds. So that would be 2 meters per second over 30 seconds, or 1/15 of a meter per second squared. I think that comes out to like 0.06 something, maybe like 0.066 repeating meters per second squared. What about if I wanted to find the average displacement, the average velocity? Well, essentially I could either do that by having this plot and circling the start and end locations and then dividing by time. So I could do V average is 190 meters minus 0 meters divided by 30 seconds minus 0 seconds. And so my V average in this case would be something like 6 and essentially a third meter per second. But how would I get that from this graph right here? How do I get my average velocity from this graph? Well, essentially what you do is you would find this total area that we just found, which was 190 meters, and you divide by the time, 30 seconds. And again, that gets you 6.3 meters per second. Okay, so now we have an example to end this video full of basically examples. And we want to know what's the displacement from 5 to 15 seconds, and also what's the average velocity in that interval. Now to answer this question, basically what we need to do is find the average, find the total displacement, which is the total area bounded by essentially the blue, and this black axis. So to do that, I can divide this into a triangle and two rectangles. This rectangle is 5 seconds by 8 meters per second. So area is 5 seconds by 8 meters per second, which is 40 meters. This one right here looks to be about 5 by 5. So area is about 25 meters per second. And this one right here would be 1/2 of 5 by 5. So half of 25 meters per second is 12.5 meters. I've put per second down here, it is just meters. Okay, so if I want to get the total displacement, delta x, let's actually do this with a little better contrast. Delta x would be 25 meters plus 12.5 meters plus 40 meters. And so the delta x for the interval, this is for the interval 5 seconds to 15 seconds, this delta x ends up being 77.5. So 77.5 meters. I also wanted to know the average velocity. So V average for the same interval should be delta x over delta t, which is 77.5 meters divided by 15 minus 5 is 10 seconds, so that is 7.75 meters per second. Okay, and so that's it. That's basically how you go about doing semi-constant acceleration. The graphs may have more intervals, but the process remains the same. So hopefully you understand this and have learned something from it, and thanks for watching.